So we are going to learn about slope fields. All right. So really what a slope field does is it gives you a sense of the infinite possible solutions to a differential equation based off of the c value, the constant of integration. All right. So basically what's going to end up happening is anytime you solve a differential equation, you're either going to get a general solution or a particular solution. The general solution could have infinitely many possibilities, but the particular solution pins it down to one particular path, right? And what we can do from a slope field is get a sense of what the overall path would be in a general sense, so that we can get an idea without having to solve the differential equation of what the solution might be in terms of a family of functions. Right, so what we're going to do here is create a table of values corresponding with this differential equation, dy dx equals 2y. All right, so you can see the independent variable here is just the y value. So I'm going to make a table with the y values and the corresponding values dy dx. All right, so the y values, if I go by the scale established here on my, they call it a lattice of points, each dot is separated by 1 unit. So it looks like I'm going, in terms of y, it looks like I'm going from -2 to 2. So -2, -1, 0, 1, and 2. So this is a proportional relationship. So all that means is that I'm just going to take my y values and multiply them by some constant, in this case 2. All right, so we're looking at -4, -2, 0, 2, and 4. All right, so all I would need to do is plot little line segments on each one of these dots corresponding with the given slope. All right, so it doesn't have to be picture perfect. If you want to get a ruler out, by all means, go for it, but it's not necessary. And all you have to do is distinguish each slope from each other slope. So for example, off the top, I see I have a slope of 0 wherever y is equal to 0. All right, so little line segments that are horizontal, because that corresponds with a slope equal to 0. All right, wherever the y value is equal to 1, I have a slope of 2. So I could just kind of wing that and just kind of give it a good little pitch, because this is what a slope of 1 looks like. All right, so I don't want that. All right, this would be what a slope of 4 looks like, so that's pretty steep. So I kind of want something in the middle. All right, so I'd be looking at something along these lines. All right, but you kind of end up defaulting back to what feels natural. So you might end up giving it a slope of, what looks like 1. If that happens, it's not a big deal, as long as your slope of 4 looks steeper than that. All right. The other values are just happening in the negative direction. So at -1, I want to go with a slope of -2. I find it's easier to turn my paper a little bit. So here I'm just turning my iPad. And so that would be my slope field. So depending on where I have a conditional value, so some sort of x, y coordinate, it might bring me into a certain part of the flow. So if I look at it like, well, this is a river, and this river has a current. Depending on where you drop your stone into the river, it might get dragged in any number of different directions. So in the example that follows, we're given the coordinate, assuming my pen wants to work, there it is, 0, -1. So if I plot that, if I assume that the river is going to carry it with the current, it's probably going to bring it in this direction here. All right. Also, at some point, it has to have a slope equal to 0, so you would imagine it's going to level out in some capacity. I just don't know if it's ever going to turn around. right? Because we don't go out far enough in terms of x to get a sense of what happens beyond this field. So that's where the solution to this differential equation comes into play. So I have dy dx is equal to 2y. That's a differential equation. We want to put that in differential form. All right, so dy equals 2y dx. All right, so we've been working on that for over a unit now. So all that is just swinging the dx over to the other side. But I want to separate my variables using a technique called, you guessed it, separating variables, by getting the x's on one side and the y's on another. So anything associated with x goes on one side, anything associated with y goes on the other. So I'm looking at 1 over y dy is equal to 2 dx. All right, so now I'm at the point where I can integrate both sides. So it's kind of like log differentiation, just in reverse, where we wanted to get an equation that was in a convenient form, and then we would differentiate both sides. Now we want to get an equation that's in convenient form and anti-differentiate both sides. So I'm looking at, instead of 1 over y dy, it would be the natural log of y plus some constant c. And on the right-hand side, instead of 2 dx, it becomes 2x plus some other constant c. All right, we'll distinguish them from one another with subscripts. But as we learned previously, we can consolidate those c values, in which case I get the natural log of y is equal to 2x plus c. Now here's where it gets interesting. So going all the way back to algebra 2, we know that the natural log of y is the same as the log base e, poor quality e, even poorer quality e. Let me fix that. 2x plus c. All right, so using Lagrange, using whatever relationship you like, just basically converting from log into exponential form, we arrive at the absolute value of y is equal to e to the 2x plus c. I'm going to continue on up top. So that plus sign allows us to split up the exponential. That actually takes us all the way back to limits. It all comes together. All right. Now, e is a constant itself. So a constant raised to a constant is going to be just another constant. So I'm looking at e to the 2x times c, otherwise known as c e to the 2x, equal to the absolute value of y. Now, this is, a little interesting. Because it turned out you didn't really have to have the absolutes on the y to begin with, but it's only in this moment that we realize that, because absolute value of y is the same as plus or minus y. Pause for dramatic effect. You got it? No? Okay. So we'd be looking at two possibilities. Y equals c e to the 2x, easy enough, or negative y equals c e to the 2x. For the right-hand equation, so left-hand equation is fine. For the right-hand equation, I can divide out the negative 1. What's going to happen when I divide c by that negative 1? Yeah, exactly. Y is going to be equal to c e to the 2x, because the constant is going to absorb the negative 1. A constant divided by a constant is equal to a constant. So either way, we end up with a general equation of y equals c e to the 2x. All right, so that's an exponential equation. That's beautiful. But we do have a coordinate that we can work with, 0, negative 1. All right, so given, little stray mark there, I can pop in a -1 for y and a 0 for x. All right, so 2 times 0 is going to be 0. Anything to the 0th power is equal to 1. This bad boy dials down to just c equals -1. And our final answer, the particular solution, is y equals negative e, because -1 times e to the 2x, so negative e to the 2x power. All right, so that is the solution to our differential equation. And if you were to plot that, along with these extra stray marks that are all over the place for some reason now, if you were to plot that, I don't know that it'll look exactly like that green curve I plotted before, but it's going to look pretty spot on.